The Indian Association of Structural Engineers, also known as ISTRUCT-E, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. ISTRUCT-E is registered under the Societies Registration Act 21 of 1860. ISTRUCT-E is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural engineering fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, ISTRUCT-E has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Kumar Ghosh, late Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Manoj Mittal, Professor R. Pradeep Kumar, and Shri Alok Bhaumik as its president. ISTRUCT-E is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, ISTRUCT-E has collaboration with various international professional like-minded associations and institutions like ISTRUCT-E, UK and FIB for strengthening global connections and professional exchange. ISTRUCT-E's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. ISTRUCT-E endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. ISTRUCT-E is actively engaged in organizing several continuing professional development CPD courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs. Seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. ISTRUCT-E's activities are widely appreciated and known for quality technical contents. ISTRUCT-E is also actively engaged in publishing its quarterly journal Structural Engineering Digest SED, code commentaries, professional guidelines, monthly newsletter, and Crossfall, a unique quarterly newsletter that confidentially reports structural failures and the lessons learned from them. ISTRUCT-E's publications are becoming popular with time. ISTRUCT-E has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, ISTRUCT-E started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. Reaffirming its commitment to professional excellence, ISTRUCT-E launched the accreditation program in 2023. This flagship initiative empowers practicing engineers to evaluate their competencies, identify growth opportunities, and strengthen the foundation for sustained professional success. ISTRUCT-E is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi to inculcate the professional culture and provide handholding to the budding engineers. Joining ISTRUCT-E offers exclusive resources, mentorship, and networking with industry leaders. Members enjoy discounted registration for workshops, seminars, and events, along with discounted membership of FIB, opportunities for certification, career guidance, leadership roles, and enhanced professional recognition. IE Struct E has its student chapters in several leading engineering institutions as well. Membership of IE Struct E is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IA Struct E is available on its website www.iastruct.co.in.
Vikas, my voice is audible?
Yes, sir. Yes, sir.
Dear friends, welcome to the webinar. Today's topic is innovative construction techniques in signature brick Delhi. The speaker is Engineer K.P. Abraham. He is a former Chief Engineer, Central Public Works Department. He is a distinguished civil engineer. He did his MTech from IIT Kanpur in 1978, and thereafter he worked for some time with the Tatas at Jamshedpur. And on the basis of engineering services examination, he joined CPWD. He has extensive experience in civil engineering profession for over 45 years. He has successfully led the planning and construction of complex infrastructure projects across India, including airports, hospitals, housing developments, office complexes, roads, bridges, memorials, and monuments. Notable projects under his leadership include the Signature Bridge and the new complex of the Supreme Court of India in Delhi. He has been associated with several BIS and IRC committees and played a key role in developing important technical publications through the Indian Concrete Institute. He currently serves as project advisor and arbitrator. About the topic, as we know that the Signature Bridge is an architectural marvel in northeast Delhi or Yamuna River to connect Wazirabad to East Delhi. It was inaugurated in 2018 and it is India's first asymmetrical cable stayed bridge and features a 154 meter tall pylon that is double the height of the Qutub Minar. The presentation details some of the innovative construction techniques adopted in the Signature Bridge Delhi installation methodology of steel and composite construction, stay cables and anchorages are presented. Many innovative construction techniques were adopted in this asymmetrical cable stayed bridge, composite construction of steel with both cast in situ and precast concrete is elaborated along with the challenges faced. Detailing required for the deck construction with precast deck panels along with integration of precast crash barriers with precast deck panels covered. Special provisions of critical locations of the bridge along with detailing for the same are explained. Now over to Engineer K.P. Abraham. Please proceed.
Can you see my screen?
Yes.
Yes.
Can you see my screen?
Yes, sir.
Please
Yes.
proceed.
And my voice is clear, I hope.
Yes, please continue.
Okay. Thank you. Good evening to all and welcome to all the participants. First of all, let me express my sincere thanks to IS30 for inviting me once again to this platform. I express my sincere thanks to all who was working behind the scene to make this happen. So today's my topic is innovative construction techniques in Signature Bridge, Delhi. Can you hear me?
Yes, sir, we can hear you.
Okay. So first of all, let me admit this is a presentation which has been shown many times at many platforms, both online and offline. It's quite possible that some of you must have seen it earlier. Kindly bear with me, all those who have seen it earlier. With this small note, let me start my presentation. Before going to the construction techniques, I'll be briefly giving about the project, its location, its construction sequences, its material used and challenges before coming to some of the interesting construction techniques. Screen is not moving.
No, sir, we are still on the first slide.
Pardon?
The slide has is
Slide
not
is
changed,
not
sir.
slide is not moving.
No, sir, no, sir, no.
Not yet.
So shall I do it again?
Yes, sir, but again.
And there's a chat.
It okay? Is it visible?
Yes, sir, please make it in full screen, sir.
Yeah, now it is moving. Okay, I will start with the location details. Most of you must be knowing the locational details of this bridge, but to those few who is still not conversant with the location, let me briefly explain the locational details of this project. You know, the Wazirabad Road, which branches out from Ring Road, Delhi, with a existing barrage over it. And this signature bridge is downstream of this barrage. Its eastern approach crossover or flyover Khajurikas Junction and merges with the Vaisarabad Road. And the western approaches gives a seamless connectivity with the ring road through a combination of flyover loops and ramps. Let me give the major features of this bridge. This is an 8-lane bridge with a length of 575 meters. This asymmetrical cable-stayed bridge is fully supported on bearings, and we have used very interesting bearings starting from spherical to rocker to guide bearings. This picture gives the major component. The P1 is on the western side, that is on the ring road side, P26 on the eastern side, and simply so the cable supported span is 251 meters. The major components, the composite deck, the steel pylon, stay cables, and the backstay cables. I will be covering some of the interesting construction techniques adopted in these major superstructure components. Briefly mention about the bridge foundation system. It's a combination of pile foundations and open foundations. 3 foundations are open while all other foundations are pile foundations. The bearings, different types of bearing are used. At the end, you have got the spherical and guide bearings and other. Most of the purity spherical bearing, except in P19, we have got a special bearing, and in P23, we have got a pendulum rocker bearing. This is the layout of the bearing for the plan layout of the bearing. All these marked space are the spherical bearings. At the end, at the beginning and at the end, we have got guide bearings. And at the pylon, we have got a special spherical bearing, a huge bearing, which I will explain subsequently. And at the backstay anchorage, we have got a pendulum rocker bearing. So expansion joint is at P1 and P26 with a with a total continuous length of 175 meters. This expansion joint at one side, modular type of expansion joints are used in these expansion joints. Now come to different superstructure components. First of all, deck. It is a composite construction of structural steel and concrete, and the steel used is mainly S355 grade conforming to EN 10025. At anchorage location, we have to use Z quality steel as a special requirement. Then we have the concrete used is both cast in situ and concrete. Then the pylon. Pylon is basically a steel construction. It's an inclined bow shape to pylon, steel pylon. It is a welded fabrication. And here, in addition to S355 grade, S460 grade is also used in critical locations. This elevation of the backside elevation of the pylon. It rests on a pylon base like analogous to a human body. It has got a leg, it has got a body, and it has got a head. At the pylon base, it is connected using a cross tie for stability. Stay cables. Stay cables, these are front stay cables. It is anchored to the longitudinal girder in the front and to the body of the pylon and the pylon side. Okay, the stand varies from 55 to 75 in each of the cables. And backstay cables, it is anchored to the middle girder and anchored to the rear side of the body of the pylon. And the number of strands in the cable is 127. It is a much more strength than to take the loads. These are the strands used in the making of the cables. The parallel system of strands are used, and you can see the technical specification here. Basic thing you have to see is it is 3-level protected. It is individually protected, it is waxed, then given an STP sheathing for durability considerations. Now coming to construction, this is a basic flow of the construction. Just to give an overall idea, generalized idea. First, we start the steel structure of the deck. After a certain stage, we start the erection of the pylon. And once the pylon comes to a certain stage, the deck slab is started. And once the slab reaches to a particular stage, cable stays are erected. Then precast crush barriers and fascia. Then waterproofing and laying of the weathering course. This is a generalized sequence of construction. So first I will start with the steel construction. This is a steel structure layout. Grid A, B, and C you can see. A is on the upstream, B is in the downstream, and C is on the middle of the structure. So these are the longitudinal girder at the grid A and C, and the middle girder at C. It is on the side girder that the cable anchors are provided. You can see it on the diagram. And cross girders are provided at frequent regular intervals over which the concrete slabs are supported. Now the pylon leg is at P19. Here the deck is widened to accommodate the pylon leg. You can see from the diagram, and the backstay anchorage is at P23. This is a cross section of the deck. The width is 35 meters. You can see the upstream and downstream longitudinal girder, middle longitudinal girder, cross girder, and the deck slab. This covers the major component of the deck slab. Now come to the erection of the steel structure. The erection started from P19 and moved towards P1 and P26 simultaneously. The erection of the steel structure. And the first erection is the pylon base. This is the photograph you are seeing is at the time of fabrication. It's a huge fabrication. Even plate thickness up to 150 mm thick was used in the fabrication, and it's a huge segment weighing 450 tons. And to fabricate it and transport to Delhi was really a challenge, both technically and logistically. And this pylon base is resting on a bearing, a huge bearing, probably one of the largest bearing ever used. This pylon base rests on this bearing. This is a bearing over which it sits. And you know there is a problem. This heavy 450-ton segment, if you directly place out the bearing, every possibility is that the bearing will get damaged. So we had to devise some arrangements to avoid any damage to the bearing while placing this segment. So hydraulic jacks are provided around the bearing. 3 numbers are provided. You can see These are the jacks. First they are placed, and this is the third jack. So this heavy segment is placed using a crane over the hydraulic jack first, and then it is slowly, smoothly moved downward to sit on the bearings without causing any damage to the bearings. You can see both the pylon base sitting on the upstream and downstream bearings, upstream piers, both the pylon base. And then after placing this pylon base, it is interconnected using a cross tie, all steel fabrications. You can see the pylon base and the cross tie in position. From the cross tie, the longitudinal girders are extended. These are the longitudinal girders which is extended both sides. You can see the longitudinal girders with the cross girders are extended towards P26, and the same is extended towards P21. This is the sequence of construction of the steel erection. And this is a cross girder, which is almost 36 meters long, and it was a really challenge to transport through ship as well as through the road. And you can see the in position, the girders, the middle girder and the cross girder. The system is extending like this one. This is a bottom view of the middle girder and the cross girder. And this is the top view of the cross girder and the girder. Here you can see studs. Studs are provided on the top of the flange, and these studs are welded right in the fabrication shop. And this is the details of the shear studs which is provided over the flanges. Now coming to the anchorage at the deck level. This is a longitudinal girder. It is on the side longitudinal girder. These anchorages are placed. These are the cable stay anchorages. It is also welded to the girder, and is welded at the factory itself, at the fabrication shop itself. We can see the photograph of the same sketch showing the anchorages. And here there is a upward force, a tremendous upward force from the cable to resist the out of plane upward tensile force. Set quality steel was used in the top flange. You can see a series of anchorages over the longitudinal girder. These are the side longitudinal girder, cross girder, and the cable anchorages. You can see the full length of the cable supported span with anchorage in position, cable anchorage in position. And this expansion joint between the bridge and the approaches, which is almost a meter gap between the two. This is the gap between the two where the expansion joints will be installed. On the other end, P26 side, this is a gap. And modular type expansion joints are used. They are installed in segments. You can see the first segment is in position, and subsequently other segment also will be placed. And this is the completed expansion joint, top view and the bottom view of the same. Now come to the pylon construction, how the pylon was constructed. Pylon is constructed, fabricated and erected in segments, various segments. You can see in the photograph in the sketch, the segment. This is the first segment, and the cross section of the first segment is like this one. It is slightly rhombus in shape. The pylon base, as I told you, is a massive section. You can see the pylon section in place, and the people are standing on the top surface of the pylon base. And on this pylon base, the pylon segment legs are connected. They are connected through welding. You can see the pylon base over which pylon leg is situated, and this is a welded connection. This is one of the very few welding we have done at site. All other welding was done at fabrication shop, and this welding was a really tough job. Of course, it is not the place to explain what are the toughness there, because our presentation is entirely different. And now comes the pylon erection. You can see the pylon segments. The first segment is being erected. These are the first segments. The first segment is placed in position, and you can see the another view of the segment in position. And they are erected in segments one by one. And you can see segments are being erected, and the fourth segment is in the process of being lifted. And the pylon legs join at a point, and that point is a kink. You can see these pylon legs are merging at a point, and this merging is a very complicated section. You can see it is being merged at this section. The pylon, as I told you, this is got a pylon leg, pylon body, and a pylon head. And this segment, this is a kink. It's a very complicated thing to fabricate, which is almost 36 meters of inclined length. You can see the details here. These are the leg merging at the point and body starting at the kink point. And the front stay anchors start at this location, and the back stay anchors also start from this pylon body. And the seating of the pylon body is, the section is like this one at the kink. This is the inclined length of this section is 36 meters long. And this has to be perfectly machined to get a proper seating of the head. And to machine it at a single setup of the machine was a real challenge. And we have to commission a special machine only for the purpose of machining these segments. You can see another view of the junction where the pylon legs are meeting. This is a photograph of the same, the inclined view, which is 36 meters long. And here is the first anchorage, which is at the pylon body. Then subsequently, pylon segments are erected one by one. And after erecting the first pylon segment, it is here you can see the pylon anchorage. After erecting the first pylon segment, we erect the cables, stay cables. And you can see the first cable in position in the first segment of the body. Subsequently, the body segments along with the cables are erected one by one. You can see how it is erected. Now come to the pylon head. So pylon head is a 20-meter height structure. It has got various platforms, mainly meant for viewing platforms, staircases, provision for stair, and a provision at the top for jibs for cleaning the facade. The section on which the pylon head sits is like this one, almost a V-shaped section. And this pylon head, which is 20-meter high, that is almost 6-meter high building, which is entire thing is fabricated, erected at the ground, and lifted as a single body and placed on top of the pylon head. You can see as a single body, it is lifted using the crane and place it over the pylon head. And this pylon head is provided with glass facade. You can see the photographs where scaffolding is provided for the purpose of giving the scaffold. You can see another view of the pylon head and the pylon body. And this is a completed pylon body with the glass facade. Now comes the cable installation, how the cables are installed. Cables comes in drums and coils, which is straightened over the plane, over the bed of the deck, before composing the cable stay. This is the cable stay cover, cable stay pipe, which is also fabricated at the sides, extended by welding. You can see the welded joint of the casing pipe. And this pipe is provide the relief to avoid or reduce the flutter and vibration during a combination of wind and rain. This is a completed casing pipe. After completing the casing pipe, the first cable strand is inserted. With this strand, the cable is lifted up to the top. You can see the case is being lifted and top and connected to the anchorage at the top. Similarly, the bottom portion is also connected to the anchorage at the deck level. You can see the deck level anchorage. You can see the first cable, the strand is connected and anchored to the anchorage at the deck level. This is the first strand, which is anchored. You can see the anchor, how it is anchored. It is anchored to the anchor block. And the first cable is in position. And now we start installing one by one stand by stand in the cables. These are installed stand by stand. You can see slots are given to make the things parallel. And this also works as a dampener. These are the stands one by one installed. And also anchorage to the anchor block at the ground level, at the deck level. And this exposed portion of the stand, which will be protected subsequently. Here you can see the entire strand in position in the cable. The close view of the same. The strands, here the strands are parallel. They are parallel. Idea of parallel is that strands can be replaced one by one at a later stage if required, without affecting the traffic on the bridge. That's why the parallel system was adopted. You can see all the strands are anchored to the anchor block below the anchor head. Okay, these are the exposed strands which will be protected subsequently. And after installing all the strands, a protective cover is to be provided, protective pipe is provided, which will be closed in the exposed portion, give us the protections. And this is a completed stay cable at the ground level, at the deck level. And this cap is subsequent, this anchorage portion is subsequently covered with a cap and filled with anti-corrosive elements like wax or other materials. And this is a completed anchorage installed cable at that location. And this is a completed cables on the front side and the same cables after the traffic is allowed. Similarly, the backstay cables are also installed one by one. You can see that installation stage in this photograph. The first cable is being connected to the top anchorage. You can see both the cables are connected to the top anchorage. And here is the bottom anchorage. The first strand is being installed one by one. These are the first strand being installed. It's a casing pipe. And this is a completed installation at the deck level. Here, fire protection is provided at the backstay anchorage because it's a very critical joint, because any explosion, any accident can create havoc if this joint of the cable is failed at this location. And this is a backstay table which is completed in position. The details at the ground level is somewhat like this, and the details at the higher level, that is at the pylon head, is somewhat like this. Now come to deck slab construction. Let us see what are the techniques adopted in the deck slab construction of the bridge. As I told you, the deck slab is a composite deck of concrete and steel. Both the precast and cast in situ concrete was used in the construction. And similarly, the crash barrier and side fascia, they are all precast components. You can see the deck slab. Here, interesting thing is deck slab is not uniform thickness. The thickness varies. At the pylon, at the anchorage, the heavy thickness almost 70 mm. Other place it is 25 mm thickness. In between it is changing. You can see the thickness variation, and in between different thickness there is slabs of various variable thickness. This deck details the precast or cast in situ slab deck, a crash barrier both side and median. This is the layout of the deck slab. He will get an overall idea of how the deck slab is constructed using both the precast and cast in situ. This shaded portion is the precast deck slab. The diagonally marked space is individual deck panels, precast panels. And then other portion which is not colored is the cast in situ portions. So cast in situ portions are mainly at pylon base and at the backstay anchorage locations. So first let me take up the cast in situ deck construction at the pylon locations. What are the special requirements? What are the detailed requirements? Which will be explained now. You can see at the P19 location, this is a cast in situ. The deck thickness is 70 centimeter thick slab. This is a detailing of the slab. You can see the pylon leg and the steel tie connecting the legs. If you see the section here, section 1, see how the slab thickness is vary. The slab thickness of the cast in situ slab is 700, while the slab thickness of the adjacent precast panel is 350. So from 350 thickness, it gradually varies to 700 thickness, and the steel structure has to be accordingly profiled to accommodate this thickness. To make it clear, let us see this 3D rendering, how this details at the pylon base. You can see pylon base, the downstream and upstream longitudinal girder, cross girders. This is the This bracket is provided to extend the deck, to widen the deck at the pylon location. And another view to make it clear. On the top of the pier, base plate is provided. It's a huge base plate, 250 mm thick. Shear plates are provided. You can see in the photograph, which is embedded in the concrete. And this is the space for installation of the bearing. And now let us see what are the forces transferred from the pylon to the deck. First of all, we should understand this pylon leg is inclined in both directions, longitudinal direction as well as in the transverse direction. So accordingly, because of the inclination, there will be horizontal force both in the longitudinal direction as well as in the transverse direction. These forces induce various stresses in the deck slab, which has to be properly designed and detailed, which will be explained now. You can see the pylon leg, which is inclined in the longitudinal direction. There will be a horizontal and vertical components. The vertical component will directly go to the pylon pier, the supporting pier. Where does the horizontal component go? The horizontal component is transferred to the deck. So accordingly, design provision has to be made in the deck to account for the influence of this horizontal force. Similarly, the inclined leg is inclined in the transverse direction also. Because of inclination, there will be again an outward force, which will create again stresses in the deck slab. This also has to be properly designed. Now, let us see the effect of this horizontal component on the deck slab. You can see this is a pylon leg. The front side is marked here. Then these are the slabs. The shaded portion is the deck slab. Now, because of the horizontal force, first of all, there will be interfacial shear between the pylon and the deck slab, which has to be suitably designed and detailed. Similarly, there will be tensile stresses in the deck slab, the rear side of the pylon. And there will be compressive force in the front side of the pylon in the deck slab. And because of the inclination in the transverse direction, there will be an outward force, which again create tensile stress, transverse tensile stress in the deck slab. So all these forces has to be taken into account and designed for. You can, to make the things clear, you can make what are the various influence, various forces induced in the deck slab from the pylon. First of all, there will be interfacial shear. There will be compression in the front of the pylon base. There will be tension in the rear side of the pylon base. And because of the outward force, there will be a transverse tension in the deck slab, which can create cracks in the deck slab if it is not properly accounted for. So let us take one by one how these induced forces are taken care of. First of all, the interfacial shear. There will be interfacial shear between the pylon base and the deck slab. You can see the pylon leg. There will be interfacial shear. How to tackle this interfacial shear? So for that one, we have provided welded shear connectors in the inside face of the pylon base. You can see in the sketch the welded shear connectors. The photograph shows the actual welded shear connectors in positions. So these shear connectors will take care of the interfacial shear between the two. You can see the another photographs of the pylon base, inside of the pylon base, where the shear connectors are provided for the full length of the pylon base, and a photograph showing the shear connectors on the inside face of the pylon leg. Now, second one is the tension at the rear side of the pylon. The tension can create cracks if not designed for, or it can separate out from the structural steel if it is not properly detailed. You can see the pylon leg here. These are the tensile forces, to how to design and detail for to take care of these tensile forces. So if you see the section here, this is a longitudinal section at the pylon base, the deck slab. This is a tensile force induced on the rear side. So we are provided, what you are provided is tie bars in the deck slab connected to the pylon base to take care of these tensile forces in the rear side. And these tie bars are connected to the steel structure using screwed socket welded to the pylon base. You can see the photograph of the rear side of the pylon and the screw socket welded to the rear side. These are detailings of the screwed socket. These sockets are used for connecting the tie bars. Now, front side, as I told you, there will be a compressive forces. And as you know, compressive forces will develop a transverse tension. In this particular case, there will be a splitting force in the transverse direction because of the induced compression. And how to design for the same. So here, what we have provided is somewhat like this one. You can see the plan details here, the pylon. We have provided confining plates on both sides of the deck and connected them, interconnected them using tie bars. The details of tie bars is like this one. You can see the confining plate. The details is like this one. This is the outer edge and this is a confining plate, and tie bars are connected through again welded screw socket. So the deck is confined against splitting forces. You can see that confining plate before concreting. This is the confining plate. This is the inside of the confining plate and the details of the screwed socket. You can see the same after concreting. It has become an integral part of the concrete confining plate. Is another view of the confining plate after the concreting is done. Now, as I told you, there is transverse forces because of the inclination of the pylon leg. These transverse forces will create transverse tension in the deck slab, which has to be designed and detailed for. And this is a transverse section at the pylon section. The deck slab, inside deck slab, where the transverse tension is developed. Here also, or you can 3D rendering will make it a little more clear. These are outward forces which create transverse tension in the deck slab. And for that one, what we have provided again is tie bars connected to the base using screwed sockets. You can see the details of the connection here. The tie bars here and the screwed socket and tie bars. These are the screwed sockets. Welded. All these screwed sockets are welded at the fabrication shop itself. Now, there is another place where cost-sensitive deck slab is adopted, and that is at the anchorage location. There also massive force will be transferred. In the pylon location, it is a downward force. At the anchorage location, it is an upward force. That means uplift force or rather tensile force which is to be provided for. You can see the P23 location, anchorage locations. This is a detailing of that section. Both sides you will see deck panel with the precast panels on both sides, and in between you have got cast sensitive deck panels. This is the 3D rendering of the backstay anchorage. The central girder, it is box section here, otherwise all I sections. This is a middle girder. This is a box section. It's a backstay anchorage and backstay cable. This is a rocker bearing which transfers the massive tensile forces to the foundation. This anchorage at the time of construction, backstay anchorages. And this is a rocker bearing which transfer the tensile forces to the pier. This is a sketch of the same. It will make things a little more clear. This is a middle girder, axis C. The top of the deck. This is the top of the anchor pier. In between is the rocker bearing provided to transfer these forces, allowing for all the possible displacement and rotations. And this rocker bearing is a combination of 4 pairs of pendulum bearings. You can see the massive forces from the cable. It's an uplift force. So it has got a vertical and horizontal component. Vertical component will be transferred through the rocker bearing, while the horizontal component will be transferred to the deck, again creating inducing various forces in the deck slab. Of course, there will be compressive forces in the rear side, the front side, and tensile forces in the rear side. So what are the effects of these horizontal forces? It is marked here. Here also, again, there will be interfacial shear between the steel and the concrete. Tensile stresses in the rear side and the compressive stresses in the front side. So all this has to be taken care of in the design and detailing. So first of all, shear connectors are provided to take the interfacial shear. Then tie bars are provided to take the tensile stress, and confining plates are provided to take the compressive forces or the splitting forces. This is the plan section of the girder at that location. These are the shear connectors provided to take care of the interfacial shear. You can see the section, the shear connectors, and the photograph of the same where the shear connectors are provided. They are provided within the thickness of the concrete. Yeah, you can see the tensile forces developed for which tensile bars are provided. The photograph shows the rear side of the anchorage where the screw sockets are provided. You can see the detail of the same. The bottom layer is connected and the top layer is yet to be connected. Now come to the compressive forces. So confining plates are provided on both sides and interconnected using tie bars. You can see the detailing of the tie bars. This is a confining plate. 28 bars are provided in 4 layers here to take care of the splitting force. This is a cross section showing the tie bars connected to the confining plate. So that is the construction of the cast in situ deck slab at a particular location. Now comes the deck slab with the precast slab system. Precast slabs of various thickness are used. Sizes of the panel varies, but maximum size was around 7.6 by 4 meter length. This was the maximum size. The slab is cast with the reinforcement projection in a U shape in all the 4 sides. You can see the panel with the slab steel projecting outside for the interconnection subsequently. After casting the slab the next day, the side is cleaned or with a wire brush to expose the aggregates so that it will have a proper bonding with the subsequent cast in situ concrete placed in between them. You can see the clean surface and you can see the same and the full panel with the clean surface. Now the panel is placed over the girders. You can see the panel is sitting over the girders. And here you can see the panel is placed over the cantilever portion where the deck is extended. This gives the general layout of the slabs over the steel structure. You can see the longitudinal girder and cross girders. It is supported between the girders, the precast panel, and the adjacent slab panel. You can see there's a gap between the panels with the reinforcement from both side meshing. And this gap is used for integrating the panel and also for getting the composite action with the steel. You can see the section after placing in position. And this is a general sequence of construction of this connection. So after placing the precast panel on both sides, longitudinal reinforcements were inserted in between the other reinforcement. Then non-string stitch concrete is placed in the joint between precast panels. And after the joint stitch concrete is cured, you get continuity of the slabs as well as the composite action with the steel girders. You can see the same joint after placing the longitudinal bars. And you can see it is partly stitch concrete. The junction is being, the joint is being concreted, stitch concreted. There are 2 types of joints. One is where where it is resting on the top flange. Second is where the top flange is not available. So here you can see the joint. The entire joint is given with a stitch concrete interconnecting the precast slabs and also making composite with the concrete. And other cases where there is no steel girder below, where a temporary platform is provided, formwork is provided, and then stitching is done. You can see the stitch is being coerced, and after the stitch is coerced, the deck is ready. Here you can see the deck which is ready, structure is ready with the stitch bone still visible. And this photograph shows all the three stages of construction. First is steel construction with this longitudinal and cross girders. Second stage is precast panel placed over the steel girders with the joints open. Joint is yet to be stitched. And third one, the joint is stitched with concrete. These are the three stages of construction of the composite deck slab with the precast slab. Now, to get this system workable, a lot of special detailing requirements were done, some of which I will explain now. First of all, there is different flange widths. You have to detail the precast slab according to the flange width. The flange width of cross girder and flange width of longitudinal girder and flange width of side girder, it's all slightly different. So detailing has to be different at different locations. Then there is play at the top flanges because the width of the top flange is varying. Now, detailing at splice joints is a very critical detailing. And similarly, supporting arrangement of the panel over the girders. The precast panel, while placing, how it support without damaging the steel girder. This is very important. So these two detailing, that is detailing at splice joints and supporting arrangement of the girder at the time of placing is very critical. And I can recall another incident where another project, the same technique was used with precast concrete composite construction, where these detailings were not fully worked out. And after a few years of service, there were signs of distress. And this lapse in the detailing could be a reason for this distress development subsequently. Then detailing at the cable anchorage locations. These are the different flange widths. You can see one flange width here only on the cross girder. This another flange width, and this side girder with still detailing requirement is still different. So the precast slab has to be cast accordingly. See the splay in the flange. The flange width, top flange width is varying. Here you can see a typical section where it is varying from 520 to 920. In between, there's a splay. So again, the precast has to be profiled in conformity with the flange splay. You can see how the precast slab is profiled at these flanges. Now second is very critical one is splice joint. How will you detail at splice joints? These are the typical splice joints. Here you can see the bolts are very close. There is no space for the studs to weld. So we have to find out some alternate at this location to provide for the studs. So what we have done is, here the bolt itself is extended as a stud. So bolt cum stud is used in that type of joints. You can see the bolt cum stud. The top portion is stud and the bottom portion is bolt. Now, next, a very important thing. This is a typical splice plate. You have got a splice plate at the top and bottom. Bottom, of course, does not create problem. But top splice plate, which is in the range of say about 50 or 60 mm thick slab, if it is not properly designed, how to properly seat the precast slab over the flange. This was a major issue. So we had to work out a detailing for the precast slabs at this location. Otherwise, you may not get proper seating, which can create havoc subsequently. So at every flange location, a recess is provided in the precast while casting itself, so that it will not foul with the top splice plate of the splice joint. And you can see a series of recesses in the precast slab to avoid the fouling and to get the proper seating of the precast slab over the flange. You can see another recess at another location of the end girder. It is a bottom view of this recess provided in the precast slabs. Now, another important thing is how to support this precast panel initially over the girders. So if you are directly supporting over the flange end, every possibility is that flange may get distorted or damaged. We should not load at the edge of the top flange. So accordingly, special provision has been worked out to support the loads. The entire load will come at the center, not at the end of the flange. We can explain, I'll explain how it has been done. So 10 mm thick flange plate is provided while casting the precast slab, which is welded between the top and bottom reinforcement of the slab. You can see a section here, a section 1, it is like this one. So 10 mm thick welded plate is provided, welded between the top and bottom reinforcement. You can see the same plate after casting of the slab. So this projecting plate will rest at the middle of the flange, transferring the entire load to the middle or at the flange, at the web location, not at the edge of the flange. At the flange, only a sealing plate or sealing rubber is provided to prevent the leakage of slurry, concrete slurry. No load is transferred to that edge. You can see the plan arrangement of the same, where the 10 mm thick plate is provided in the precast slab. See, the same is provided at the time of providing the reinforcement itself. You can see the same after casting of the slab, and holes are provided in this plate for the longitudinal reinforcement to go through. This is the joint where the steel plate is resting at the center of the flange or directly transferring the loads above. And this is the same photograph after providing the longitudinal reinforcement. And here, this plate is resting. For resting of this one, a steel plate is welded at the location to support the steel plate. So it is resting on this steel block, which is welded to the center of the flange. Okay, with that one, let us come to a detailing around the anchorage. How to place the precast slabs around the anchorage. That was a real challenge. And this anchorage, this is a deck anchorage. This is a series of deck anchorages you can see. It has got all the three axes. It is varying. The angle is varying. The vertical angle, the tilt angle, the horizontal rotation. And for each one, these three angles will differ depending on its location from the pylon leg. So everywhere, the detailing has to be individually carried out. You can see a typical sketch of the longitudinal girder and the cable anchorage. If you section here, you see it is inclined towards the deck. There's an inclination. This inclination is also varied depending on its location. It's a photograph of that tilt of the anchorage with reference to vertical axis. Now there is a rotation. This is the cable anchorage. This rotation also will change depending on its location. So everywhere, wherever there is a possibility of fouling with the concrete, proper detailing has to be worked out. So we have to provide recess at every locations where the steel fouled with the concrete in advance. This is the steel structure at the location of the girder at the anchorage. You can see the location. This is a photograph before placing the concrete slabs. This anchorage, you can see even horizontal studs are provided to integrate with the concrete. And this photograph shows the same with the precast panels all around it. This is another view of the precast panel all around the anchorage. You can see the recesses are provided wherever the flange or any other component fouls with the concrete. This gives overall view of this slab layout around the anchorage. You can see how it is placed and the joints are visible. And these joints are subsequently stitch concreted and you will complete the construction at that location. So now we come to the last part is the crash barrier. Here the issue was how to integrate a precast crash barrier with the precast deck slab. I will briefly explain that one. You can see the median crash barrier and side crash barrier. See how it is done. While casting the crash barrier, we provide a hole and a pocket. Hole for the bolts to go through and pocket for subsequent sealing of the same. You can see the detailing here. The bolt passed through a hole provided in the crash barrier and a pocket to subsequently close it. After tightening the bolt, these holes are pockets are filled with the concrete. Similarly, for the side crash barrier, after tightening the bolts, it is filled with the concrete. These things are cast in segments. You can see the side crash barrier here and the central crash barrier here. This provided with a socket and a hole, and a hole. You can see the hole and the here. And before stitch concreting, these bolts are welded to the top of the flange. You can see the bolt is projecting above the flange. And the same thing after stitch concreting, you can see the bolts are projecting above. And segments is lifted and placed in such a position, such a way that this bolt will pass through the hole. You can see the bolt is passing through the hole. Both the pockets are visible. And then it is tightened with a plate washer. And after tightening the bolt, it is filled with the concrete. You can see the photograph when the crash barrier is ready. So the next stage is, the final stage is deck waterproofing. The entire deck is waterproofed using APP membranes. This for durability considerations. And this is the final deck where the traffic is running. With this one, let me complete my presentation with thanks to all who listened to the presentation. Thank you very much.
Excellent presentation, Abra. Before a few questions will be asked from our listeners, I have 2 or 3 things which listen and let me know. The first question, what arrangement of this monitoring system after the operation, because the life of structure is over 100 years. What methodology that we have contemplated in monitoring the safety of the structure? The second point is, the project was executed by Delhi Tourism Transport Corporation. What are the measures of maintenance and of the structure and the monitoring being adopted during operation and maintenance of this important? The third one is safety during construction. And the last one is the lot of steel we have used, the corrosion prevention of the steel. I mean, please explain a few things before the other person will ask you a few questions. Abra?
Whatever I can understand from your question, first one is the quality assurance. There was an in-house quality assurance, plus there is a third-party assurance also, mainly for the fabrication and erection of the steel structure. Second question, can you repeat? I'm not able to recollect.
This structural monitoring by instrumentation, we have used number of sensors.
Structural monitoring was installed, but unfortunately, what I could gather, of course, I am not with the DTDC anymore, that system is not fully functional, but PW is taking initiative to make it functional. That's what I could gather. And that question was?
Then this maintenance now, of course, the Delhi PWD will take over. This is what you told me. Now the question that I asked you, the safety during construction, including the safety of the enabling structures.
Safety of the structure.
Enabling structure and the structure both.
Enabling structure was at the time of construction. This was all designed and
right.
constructed. So to take the safety considering the aspect. And secondly, now regarding the PW, to my knowledge, it has been already taken over and they are already on the job to do a regular and proper maintenance and upkeep of the structure. Okay.
And then finally, corrosion prevention of the steel, that a lot of steel structure is used. What are the corrosion prevention measures?
We have got a system of corrosion prevention, mainly coatings. A special system of coating was provided. I don't have the detail now. Probably it is available with DTDC.
Mhm.
Okay.
So thank you, Vikas. Please, one by one, what are those questions that persons want? Please.
Yes, sir. Yes, sir. Yes, there are a few questions. First question is by Mr. Rajesh
Can you
Gupta.
make it louder? It's
Uh,
very difficult for me to hear.
Louder, please.
One second, sir. Yeah, the first question is by Mr. Rajesh Gupta. I recall that a comprehensive structure health monitoring system with various instruments was planned for the signature bridge. Could you please elaborate on the types of instrumentation that were ultimately installed? Also, are these instruments still operational and is continuous monitoring and data analysis being carried out as a part of the bridge long-term health assessment program?
This was installed. That's what I know. Or comprehensive monitoring system was involved, but unfortunately, it was not functional for quite a long time. Now PWD is taking initiative to make it functional. That is why my information. Okay, thank you.
Okay. Yeah, thank you, sir. Mr. Abdul Raut asked, for young engineers, what technical skills and software knowledge are most important for working on large bridge projects today?
Knowledge, basic knowledge of the bridge is essential, and especially cable stayed bridge are far and few in our country. Probably, I don't know whether any institute is specifically giving a curriculum for long span bridges. I'm not aware. Probably, education institution can think about for long span bridges separately courses. And software, I may not be able to comment. Probably younger generation will be better in handling the software. Thank you.
Sir, Mr. Ali Jahedi asked, why the pylons leg constructed in inclined shape?
See, that is an iconic structure. It's a design they want. The owner wants something unique. To make it unique, this shape was provided. It is almost resembling the Namaste shape. That's why. It is a specifically chosen shape because of the uniqueness requirement.
Thank you, sir. Mr. S.M. Monirul Raman asked, have wind tunnel tests been carried out? If so, what types of checks were performed?
Wind tunnels were carried out. I don't have the details of the wind tunnel test carried out. Probably you can get from DTDC. It was done in SCRC, to my knowledge. SCRC Chennai. That's what they are done. Okay, thank you.
Thank you, sir. Mr. Venkat Gavaraj asked how the load effects of strand replacement will be considered in design without interrupting traffic.
It's a parallel system. Stand by stand, it can be replaced, and maybe as a precautions, some extra requirement stands were provided. So one stand can be taken out at any time without affecting the design requirement.
Thank you, sir. Dr. Dulal Goldar asks, please discuss difficulties faced during construction of the signature bridge.
Oh, there's a lot of difficulties. I think that itself requires a presentation. It cannot be dealt with at this point.
So, thank you, sir. Mr. Samir Bendre asked, is cable vibration due to wind considered? And other question is rain wind effect on cable considered? And the last question of his is, what is the natural frequency of the deck?
This was considered, and also enough dampeners were provided, internal dampeners provided, take care of the things, and the vibration to a large extent will be reduced because of the profile provided over the casing pipe. Other one, last question, I may not be able to comment. Thank you.
Thank you, sir. He again asked, is fatigue assessment done?
Yes. This is a part of the design. All the fatigue assessments were done.
Thank you, sir. Mr. Muhammad Yasir asked, how is the tie bars are traced to the confining plate? Is it from the other end?
That's what I explained. We have provided the screwed sockets, which is welded to the confining plate, and in between, inside of the confining plate is connected through the tie bars. Okay.
Thank you. Yeah. Mr. Venkat Gavaraju asked, is the transfer shear at pylon base registered by concrete deck and transverse girder by composite action?
All are taken by composite action. Even with the composite action, there will be tensile stress developed in the concrete deck slab. And that is why these special portions were provided. Okay.
Okay, sir. Mr. Sunil Mukti asked, sir, is the stitching concrete is normal cement concrete or polymer modified epoxy concrete?
No, it is only shrinkage compensating compounds were used mainly. Only for shrinkage effect was controlled, nothing else.
Mr. Venkat Gavaraju again asked, is the design and detailing of deck slab done by strut and tie theory?
Design I may not be able to comment. It is basically done by a German consultant. I may not be able to delve in detail the design requirements.
Thank you, sir. Mr. Sarvesh Kumar Jain asked, what precautions were adopted for any strong wind or seismic activity during construction?
The seismic activity is not a major issue here, is because a very flexible structure. And as I told you, wind analysis and wind studies were done, and the system was designed for the wind forces as per the codal requirements.
Thank you, sir. Mr. Runal Kanti Bhattacharya asked, will you please explain regarding the stressing sequence of the cables, including stages?
See, this is also a long process. We cannot tell these things in one word or two words. This requires separate probably discussion or presentation. There was a standard operating procedure given by the consultant how to fix and stress these cables at various locations. Thank you.
Thank you, sir. Whether Mr. Muhammad Yasir asked whether temporary scaffolding system is reused, was this not challenging in rainy season?
Reused in other projects, reused we do not know because the contractor takes away the structures. And most of the things, whether temporary structures are pylon and vertical cranes, this all can be reused. There's no problem. Okay,
thank you, sir. Mr. Sayyid Munawar Ali asked many questions. I read one by one. During the installation,
question you ask.
Okay. He asked, what is the recommended method to replace or repair a broken, damaged stud bolt?
Broken?
Damaged stud bolt.
Stud bolt damage is more. It's already embedded in the concrete. There's no question. Unless the concrete is damaged, the stud cannot be damaged.
Okay. He asked, should the repair be carried out in accordance with any specific standard or manufacturer's recommendation? Repair of surrounding concrete, pull-out house test, load testing, or newly installed.
Repair comes only when some damage happens, not at the construction stage.
Right.
Yes, sir. I'm taking one last question. What are the maximum and minimum cable forces expressed as percentage of the cable's ultimate tensile strength?
I may not be able to comment that one because all our design data is not readily available with me and I cannot recollect also. Probably you can get from DTDC if required.
Okay. Thank you, sir. Thank you. Dr. Dhawan, sir, you please care.
Finally, I'll conclude by saying that such a complicated thing, bridge composite construction of steel with both cast in situ and precast concrete is explained so beautifully with the giving detailing for the deck construction with precast deck panels along with integration of precast clash barrier with precast deck panels covered in your talk. It is an excellent presentation. I'm sure the participants must have gained sufficient knowledge and they will apply this in the future projects. On behalf of the Institution of Structural Engineers and my personal behalf, I thank Engineer Abraham Saab for sharing knowledge and experience and sparing valuable time for giving such a elaborate, complicated topic to the benefit of young engineers. Thank you once again, Abraham Saab.
Thank you. Thank you very much.
Thank you, sir. Thank you.
And now let's conclude.
Okay, sir. Thank you.